Okay, now I want to go through how each of the sensors works so that you'll understand better how the system goes. As I touched on earlier, the master inverter is to tell the GCU how much load is on the unit. As I mentioned briefly, this works very similar to what is referred to as a speed air density system, only it does not have a manifold absolute pressure sensor. And the manifold absolute pressure sensor would tell a standard gasoline engine pretty much how much load is being applied to it. The master inverter is able to tell the GCU how much load is applied to it by pretty straightforward math. This is they call it in a model EU7000, it's 6,500 watts peak and 5,500 continuous. If at 6,500 watts, you would multiply that by 1.341 to give you the horsepower, so 6,500 watts. Would be 8.71 horsepower. And that would be mechanical horsepower. This this generator's rated speed is 3,600 RPMs. And it has a circuit in it so that if it exceeds 3,900 RPMs for more than 3 seconds, it turns on the overspeed fault light and shuts the unit down. If it exceeds, I believe it is 4,100 RPMs or possibly 4,000 RPMs, it shuts the system down immediately without waiting for the 3-second interval. It is 4,400 RPMs. So in other words, if it fails the first shutdown sequence, it shuts down instantly at 4,400 RPMs. Interesting point about this engine is it produces 19.4 foot-pounds of torque at 2,500 RPMs. And then they give you 11.5 horsepower at 3,600 RPMs, which is a little bit deceiving because this engine actually has a very broad horsepower curve, although the torque curve falls off. And let me show you real quick. We're going to say that this is the center line of a crank. And here is the connecting rod. So of course the flyweights of the crank. Connecting rod goes up to the piston. This engine has an 88 millimeter bore and a 64 millimeter stroke. And that would be the extreme limits of the stroke. So 88 millimeters is going to be 3.46 inches. And the stroke would be 2.51 inch. If you wanted to convert the torque in foot-pounds of torque to give it the horsepower, the formula is straightforward. And it'll allow you to see how flat the power curve is on this engine. So if you take the distance around, because it's going to be applying 19.4 pounds pressure to the rod for 360 degrees of rotation. 360 degrees of rotation, if the stroke is 2.51 inches, divide that by 2, because the radius would be half of the full distance. So 2.51 inches would then be 1.25. To get the distance around, it would be 2 pi r. So 2 times 3.1459 times 1.25. So 3.14159 times 2 equals 6.28 times 1.25 is equal to 7.85. So now we know the distance around. So in order to give yourself 19.4 foot-pounds of torque at 2,500 RPMs, to figure the horsepower on this, you'd take the original 19.4 foot-pounds of torque times the distance around, because it is applied for 360 degrees, which would be 7.85, which would give you 152.9. Then multiply that by the RPM of 2,500 RPMs. Which would give you 380725. Then keep in mind, 1 horsepower is 550 pounds per second, and there's 60 seconds to a minute. Since we're working in revolutions per minute, we want to multiply the 550 times 60, which will give you 33,000. So divide this by 33,000, and you get that you have 11.53 horsepower at 2,500 RPMs. You have 11.5 horsepower at 3,600 RPMs. And if you wanted to work the formula backward, then you'd see that your 11.5 horsepower comes out to 13.2 pounds of torque. So the peak torque is at 2,500 RPMs, and it develops 19.4 pounds of torque. And I know I have these written backwards, so it's a little bit confusing. As the engine RPM increases to 3,600 RPMs, the torque falls off from 19.4 pounds all the way down to 13.2 pounds, but the horsepower remains very consistent. Keeping in mind that the horsepower to kilowatt is 1.341, so you divide the 11.53 horsepower and you get 8,500 watts. So since this generator is 6,500 watt peak, you have quite a margin of error. The engine is capable of producing quite a bit more power than the output on the generator would need to be. However, the inverter unit is not 100% efficient because you're going to be generating 3-phase full wave, rectifying it to DC, then inverting to DC through pulse width modulation to an AC 125 volt, 2-legged 60 hertz system. And we'll explore that later when we get to discussing the generator portion. But at any rate, what this does is it allows you to see that the master inverter unit can accurately report back to the GCU how much power is being made by the engine, or how much of a load is on the engine. I don't want to spend too much time on that because that's the sort of thing that you can get really deep into. Next, I want to do the ambient air temperature sensor and engine block temperature sensor because they are both temperature sensors and they both work on the same principle. We cannot validate the ambient air temperature sensor because it's mounted in the ECU, and I don't want to start playing around with heating it up, cooling it down, and so forth. But we can verify Honda's numbers on the engine block temperature sensor. The block temperature sensor is a pretty straightforward circuit. They apply plus 5 volts on a spout lead from the GCU to the sensor. So the GCU will have plus 5 volts as a reference. It'll go through a fixed resistor. My artwork is not real super good. In fact, it's really super bad. Then you have a lead that goes to the engine block temperature sensor. Inside the engine block temperature sensor is a variable resistor that changes resistance as the block temperature goes up, and this goes to a ground lead. Now, if you're applying 5 volts to this, and this resistor is 1 ohm, or say 1K, Honda gives you illustrations in their manual of this being 1K and this being 1K, then you know that the voltage drop here and here are going to be identical. However, the fixed resistor at 1K, and according to Honda, at negative 25 degrees Celsius, the resistor in the engine block temperature sensor is going to be 19.5 K. And you can check their math on this. They're saying that your voltage drop here, as measured by the GCU, is going to be 4.75 volts. So if you take 1K and 19K, that's 20K, no big deal. You're going to take, let me see here, quick, I is equal to U. So the voltage divided by the resistance will tell you the current through it. The voltage of 5 volts divided by the resistance, which is 20,000, gives you 0.00025. Will give you, and that's your current. Multiply that by the 19,000, and it gives you 4.75 volts. So their illustration is correct. And that's pretty straightforward and simple. If you want to look it up, it's called Ohm's law, which is I is equal to E over R, or current represented as I is equal to voltage E over R resistance, or voltage is equal to current times resistance. This is their figures for the cylinder head temperature sensor or engine block temperature. The ambient air temperature, like I say, I don't have any way of testing that or verifying that right now without the Dr. H onboard scanner. The barometric pressure sensor works with a silicon diaphragm, and it works on the same principle. As the pressure is increased on the silicon diaphragm, atmospheric pressure that is increased on the silicon diaphragm, it uses the same circuit where the ambient air temperature sensor and the block temperature sensor use temperature to modify the resistance of the resistor. The barometric pressure sensor will use barometric pressure on a silicon diaphragm to alter the output voltage, and it works through the same reducing circuit. Let's take a break for just a moment. Next sensor I'm going to cover is going to be the crank position sensor. The crank position sensor is a magnet wound with a coil around it. You're probably familiar with an AC sine wave. And that's what the single-phase AC output on the single-phase generators looks like. And this is typically what's caused by a magnet passing by a coil that is wrapped around a steel core. The crank position sensor, we would need to, that is used to determine the precise location of the piston or the crankshaft in top dead center. We'll say here's the center main bearing, and then here's the rod bearing out here, and then you got the pork chop flyweight rod going up to the piston and the cylinder walls. But your crankshaft can be any position, and you've got a flywheel on the end of the crankshaft with a trigger. And when the trigger passes by the pulsar coil, it creates a signal. And this is to give it precise data on where the position of the cylinder or the piston and crank is, so that it knows exactly where to fire the ignition based on engine RPMs. It does not have a distributor with a centrifugal governor to determine the spark. You'll notice that this waveform, because it is very smooth and progressive, where exactly is top dead center? Or where exactly is the reference point? You don't know if they're trying to go climbing or as it descends and it exactly crosses the center line, which would be a good reference if they could report it. However, the crank position sensor does not use a coil wrapped around a steel base triggered by a magnet. It uses a coil wrapped around a magnet. And then on the flywheel, there is another steel tooth on a reluctor wheel. The waveform that produces looks like this. As the reluctor wheel comes close to the core, the voltage starts to climb. And that is because the magnetic field is compressed around the coil. As soon as you get perfect alignment between the reluctor wheel and the magnetic field, there is no movement of the magnetic field. And remember, movement of a magnetic field around a current carrying conductor is what it produces an electrical voltage. When there is perfect alignment, the voltage drops. And then, as it moves away, there is again movement in the electric output. So the waveform looks like this. When you see a waveform like that, you're going, now I can tell where the trigger point is. The trigger point is right here. Not too hard to find. And that's why they use this as a crank position sensor. Okay, let's go ahead and take a break for a moment. Okay, the next sensor that I want to do is the generator itself. And the generator is three-phase full wave, and they only use this, according to Honda, for referencing the engine speed. And of course it puts out a standard sine wave. Being that it's three-phase, it will actually look like this. When you look at it on an oscilloscope. But at any rate, Honda says that you're going to get 10 pulses per revolution. And it uses this to determine the engine RPM. The next sensor would be the throttle control, or excuse me, the throttle position sensor or TPS sensor, which I explained earlier. It does not have an actual TPS sensor, but the GCU knows what it set the throttle stepper motor to. So the signal that it used to send to the stepper motor is what it uses, and it presumes that the stepper motor did indeed execute the movement that it said to do. Now, okay, the last sensor that I'm going to go into is the exhaust gas oxygen sensor. The exhaust gas oxygen sensor is probably the most important sensor on it, because it is the one that goes along and makes corrections based on what the actual output of emissions are. All the other sensors are used to calculate the theoretical perfect amount of gas. The oxygen sensor basically goes along and grades the test. The oxygen sensor actually creates a voltage of between 0 and 1 volt. And the higher the voltage, the richer the mixture; the lower the voltage, the leaner the mixture. And here's how it works pretty much. I am not an artist, and I don't want to be an artist when I grow up. So we're not going to grade it on photo or on art ability. You've got the hex flange that you would screw it in the exhaust manifold, the threaded area, and there is an air intake on the inside. But through the inside of the oxygen sensor, you've got a channel that runs all the way down. There is a metal sleeve that's perforated, and that's to allow exhaust gases to get in. This is zirconium dioxide. When the generator, when your generator or your engine is running, exhaust gases, and here's your exhaust pipe, exhaust gases are passing by here. Fresh air is going into the center. As the exhaust gases pass by, some of the exhaust gases get into this area right here. A voltage is created when oxygen from the oxygen-rich environment goes to the oxygen-poor environment, and it creates a voltage within the zirconium dioxide. So if you have very little oxygen in this area and tremendous amount of oxygen in this area, it'll create a higher voltage. Very little oxygen means that you probably have more fuel and it has burned every little bit of the oxygen, so that would indicate a rich position. A lean position would be when there's almost the same amount of oxygen in the exhaust as there is in the fresh air. Therefore, you get very little transfer of oxygen molecules from the fresh air tube through the zirconium dioxide to the exhaust chamber. It's simply a chemical reaction. Simplest terms would be like a battery. However, the oxygen sensor has to get to approximately 600 degrees Fahrenheit to go into closed loop operation. The automotive guys already know that, and that's, you'll hear them use the term closed loop or open loop operation. Open loop means that it is working on the pre-described strategy. Closed loop means that you now have the oxygen sensor coming along and grading the test. This oxygen sensor on this is a single wire oxygen sensor, which means it is not heated. You'll see some oxygen sensors with 2 extra wires on them, and that's usually a heating element, which gets it into closed loop operation a little bit more quickly. The main power obviously just powers up the GCU. The oil level switch is just an on-off switch. It tells the GCU that, hey, you're out of oil. And then, of course, the starter switch is simply the button that you press. We'll go ahead and take a break here, and then we'll start discussing the output.